So after you've covered orders of reaction and you're pretty comfortable coming up with these rate equations, where rate equals some constant, the rate constant times the various concentrations that are involved in the reaction and that affect the reaction rate. Now you've got to try to figure out, well, what's a possible mechanism that could explain this rate equation? How does this reaction actually take place? Now, as far as I can tell, you don't actually have to suggest your own rate mechanisms, reaction mechanisms, but you do have to be able to evaluate reaction mechanisms to see whether or not they match with the rate equation. It's actually easier than it sounds, and let's just review a couple of the key ideas behind them, and then we'll give them a try. So remember that the most important step in terms of kinetics, in terms of how fast reactions happen, is what we call the rate determining step. And that really only the rate determining step matters in terms of the overall reaction. And that's because that step has the highest activation energy and it sort of bottlenecks every other step. And so whether or not the rate determining step is first, second, or third, if there were 3 steps, plays a big part in where the different reactants are involved in the reaction. Okay, so essentially the key takeaway for reaction mechanisms is that really only the RDS matters. Any reactant involved after the rate determining step will not show up in the rate equation. Now, one thing here is that even though you might have one where the rate determining step is second, and so things involved before that, you might think that they don't show up in the rate equation. However, with rate equations, you never have intermediates in the rate equation. So rate equations do not contain intermediate concentrations because those can't really be measured or known. They're just things that are formed partway through the reaction. So we can only really show concentrations of reactants. So because rate equations don't show intermediates, if, for example, the second step is the rate determining step and it involves an intermediate, then the intermediate will get replaced in the rate equation by the reactants that formed it. That sounds a little confusing without examples, so I'll try to clarify that in just a second. So rate equations do not contain intermediate concentrations. Intermediates involved in the rate determining step will be replaced by the reactants that form in the rate equation. Okay, so those are sort of the 4 takeaways about rate reaction mechanisms. Let's see it in practice. Okay, so for this one, if we look at the rate equation, we can see that the reaction is second order with respect to nitrogen monoxide, and it's first order with respect to hydrogen. Notice that hydrogen in the stoichiometric equation is in there twice, but it's only in the reaction mechanism once. And so immediately one takeaway that I would have is that H2, or one of the hydrogens, must be involved after the rate determining step. Because if it's in the if both were in the rate determining step, they would both show up in the rate equation. Or if they were both involved in the rate determining step or before it, they would show up in the rate equation. Because only one hydrogen is there, one of the hydrogens must be there after that rate determining step. Okay, so here is a possible mechanism, and let's say you were presented with this on the IB exam, and they said, okay, let's see whether or not this possible mechanism that's being suggested, let's see whether or not it matches the rate equation. So what it's saying is that in the first step, perhaps nitrogen monoxide reacts with a hydrogen molecule, creates a nitrogen atom and a water molecule. Now, this nitrogen atom, that's what we mean by an intermediate. Notice it's not anywhere in the actual stoichiometric equation. It's something that they're suggesting gets formed partway through, and then it immediately gets used up in the next step. Okay. So then they're saying that N reacts with NO, makes N2, and then that also makes an oxygen atom. Now again, oxygen atom is a different intermediate, also not in the stoichiometric equation, something that's formed and then immediately consumed in the reaction. Okay. Now remember, these steps are being presented to you. You're not coming up with them yourselves. You're just trying to evaluate how well they match with the rate equation. Okay, so if the rate determining step is first, then the only one of these three steps that matters is the first step. Okay, let me get here. Yeah, there we go. Okay, so here's the first step. This is really all that affects the rate. Anything after the rate determining step has no impact on the rate determining step. And if we think about affecting a rate, we really just care about the things involved, the reactants, right? So based on this first step being the rate determining step, my rate equation would only have a first order for NO and a first order for hydrogen. So every time that a reactant is involved in the rate determining step or before it, if it's involved once, that's what it means to be first order. If it's involved twice, that's what it means to be second order. And if it's involved not at all, that's why something would be zero order. So because nitrogen monoxide is involved in the rate determining step one time, I would consider nitrogen monoxide here to be first order. Because hydrogen is involved one time, that would mean hydrogen is first order. So if we look at our original rate equation, and then we look at this possible mechanism, it would look like this. So based on this mechanism and this first step being the rate determining step, then this is the rate equation that we get. So that does not match what we know from our data or what was given to you, this rate equation up here. So it doesn't match. So that means this first mechanism, maybe the mechanism isn't wrong, but the rate determining step is not the first step if this is the mechanism, because it gives us this rate equation, and this rate equation doesn't match the one that we're given in the problem. Okay? So let's move on to the next one. In this case, it's the exact same mechanism, but now the rate determining step is here at second, okay, which means we're going to look at this equation. So these things matter. Okay, well, that would mean that the rate determining step would be NO and N, because those are the two things in the rate determining step. Those are the only two things that really matter for the rate. However, we can't have an intermediate in our rate expression. So what you have to do to replace it is you say, okay, well, here's N. N was formed in the first step. So what does N depend on? Well, the formation of N depends on both NO and H2. So I can rewrite this rate equation like this. Instead of N, I write NO and I write H2. I simply replace it with the reactants that formed it. And then if I rewrite that, if I simplify it, I actually get my original rate equation because the NOs are now squared. And so now you can see that the rate equation, this mechanism, this proposed mechanism, with the second step being the rate determining step, this is a perfect match for the rate equation. It doesn't mean for sure that this is how the reaction happens. It just means that this is one suggestion that matches the data. The NO and the N are really what affect the rate. They would be both first order if this was the only step, but because N is an intermediate, you go back to the first step and you say, okay, well, which reactants formed N? These each formed N, and you put those in for N in the rate equation. And then you combine terms and simplify. And so this would be the rate equation. It matches the one we got from the data. If we're doing this last one, and the third step was the rate determining step, then your rate would depend on H2 and O. But since O is an intermediate you'd go back here. What does O depend on? Well, O depends on those two. And since N's an intermediate, and what does N depend on? It depends on those two. And so in the end, you'd get a rate equation that was NO squared and H2 squared, and it would be a fourth order overall. And again, this does not match what was given to us in the question. So of these three choices that I showed, the middle one, the middle mechanism here, where the second step is the rate determining step, that is the big winner. That's the one that actually matches the data. Okay, so we can do this again. Here's a different reaction, same type of rate equation, third order overall. If we look at possible mechanisms and try to evaluate them, you can pause the video and see if you can come up with what's the rate equation based on this proposed mechanism. So saying it takes place in two steps, and the first step of which is the rate determining step. So if you want to try it, pause the video, and then I'm going to go ahead with my answer. Okay. I hope you had a chance to check now. So if this first step is the rate determining step, then this would be the rate equation, because the rate would only depend on NO and NO. It would depend on NO's concentration twice, because it's involved twice in the rate determining step, which would explain why it's second order. However, there'd be no oxygen in the rate equation because oxygen comes after that. So oxygen wouldn't affect the rate. So we know that this one can't be right because oxygen is apparently involved in the rate. It's in the rate equation. So we already know the second step must be the case, must be the correct one. In this one, as it's written, we'd get N2, O2, and O2 in the rate determining step, and then we'd say, okay, but N2O2 is an intermediate. What does that depend on? It depends on NO, and it depends on NO twice. And as a result, it depends on NO squared. And so this one gives us the correct rate equation, the one that was given to us in the question, or the one that we figured out from the data. And so therefore, this is the correct mechanism. Okay, I think you guys get the idea. We'll have other ones that we can try in class. I'm gonna skip over these and just get to one other idea, which is that catalysts, although they don't show up in the overall stoichiometric equation, they can be involved in a mechanism because catalysts can react and then be reformed in reactions, and so net, they don't show up in the stoichiometric equation. So for example, this is the reaction that was involved in the elephant toothpaste demo. It's hydrogen peroxide using iodide ions as a catalyst, and the reaction produces a lot of oxygen gas, which is what creates all the bubbles so quickly. And the iodide makes it happen really fast. Well, how might that be? How might that happen? Well, if the iodine is involved in the first step and causes the hydrogen peroxide to break apart and create this intermediate, then that intermediate can go on to react with another hydrogen peroxide, producing water, oxygen, and reproducing the I minus. So if you add up this equation to get the overall stoichiometric equation, you notice that the I minus cancels, the I minus cancels, the IO minus and the IO minus cancel. And if you add this up, you get two H2O2s, makes two H2Os, and one water. So you do get the original stoichiometric equation. Now, if you want to know what's the rate equation from this, well, it depends on what the rate determining step is. If we say that the first step is the rate determining step, then we get a rate equation that only depends on that first step. So we'd say the rate equals K, H2O2, and I minus. Now, I minus is not an intermediate, right? I minus is a catalyst. So you can know its concentration, and therefore it can end up in the rate equation. So reactants can end up in the rate equation, but also catalysts can end up in the rate equation. Just not these things like the IO minus, the intermediates. So based on this first step being rate determining step, only the two things involved there would matter, and so this would be the rate equation. If the second step here is the rate determining step, then, well, first we'd say that the rate equals IO minus, and it equals H2O2. But because IO minus is an intermediate, we would look at what formed IO minus, and that would be these two things here. And so we'd end up with I minus and H2O2 squared. And so I didn't give a rate equation to match here on this page. It was more just thinking about how could you see something in a mechanism that's not actually in the equation. It's because it can be used up and reacted and also reproduced, and that cancels it out of the overall equation. Yet it can be in the rate equation because it has an influence on the rate. Okay? And this is just one more example of something that you'd see in organic chemistry, or that we will see in organic chemistry reactions. There are two different organic mechanisms that you learn called SN1 and SN2, nucleophilic substitution, that is either unimolecular or bimolecular. And it's just about rates. It's the reason why they're called that is based on their kinetics. The first mechanism involves a two-step process, and the first step is the rate determining step. And so because this first step is the rate determining step, and there's only believed to be one particle involved in it, you want to put a rate equation that is equal to just this molecule, this halogenoalkane, whatever it happens to be. The other reactant in the mechanism is hydroxide ions, but they have no effect on the rate when it follows an SN1 mechanism. Whereas in the second kind, SN2, follows a different kind of mechanism, only believed to take one step, therefore it has to be the rate determining step. And there's evidence that both hydroxide and the halogenoalkane have an effect on the rate, and so this is the rate equation. And so when we learn SN1 and SN2 reactions in the not too distant future, that's where the names are coming from. A rate where the rate determining step involves one molecule, or where the rate determining step involves two molecules. And then there's more practice here. We'll check out some more in class. But that's reaction mechanisms and evaluating reaction mechanisms.